Hang on, let me bring them in. I don't ever drink that, so admit all. But I will drink slime. So when we get into studying fermentation, I can definitely talk about that. And we do make our own cider. And to do that, you have to go, Michael went with us last time, but you have to go up to the mountains and get like flash pasteurized cider, because if you get the thoroughly pasteurized stuff from the store, it's too bug free, and it's no good. Okay, let's see. Hi Shannon. Hey Jack. Sorry we were a minute late. We were balancing chemical equations. So after we wrapped up lab, that's what we did. We practiced equations for a bit because everybody needs a little more practice at that. I've got your papers, but I'll do that next week when you're back. And the last one. So I think most of y'all heard that, in case you didn't, our class is permanently reduced now by 3. The Lovings have decided not to return for second semester. So that's the 2 girls out here, and then Trav was supposed to be in the other class, but he didn't show up much. And then we also lost Alex online, which was, that was a bummer. I guess they thought it was like an option to do 1 semester. So I don't know. She'll figure out how to finish up the credit on her own, I guess. So she's out. So it's just now this crew, and we technically don't have anybody online for this level class anymore. So what we'll do is we'll just go ahead and do it anyways. Sydney is, she's just not been feeling very well. So I know, it makes me sad that she's sick, but she's not got, it's not like your house. She didn't get COVID or anything, but she's feeling just under the weather. I asked Jules how it was. I said, Jules, you have to tell us everything. And so she did. But we're glad that you guys are back. And I was telling Jules, I thought it was, well, not funny that she's sick, but my priest's wife is sick. She's got COVID right now, but he made me laugh at what he said about her, because he said, well, Terry's quarantined upstairs in the bedroom behind the door of shame. He said, we're passing food through the door like she's a prisoner, which I thought the whole image was hilarious to me. So, oh God, let's go see what we've got for today. So we are doing a lot of this energy stuff, energy transferring, energy moving from point A to point B. How do we get from one state of matter to another? There are too many windows open on this screen. Go away. You can go away too. Man, okay, there we are. I can see today. So changes of state and equilibrium. This is kind of where we need to be today. And this stuff is a little abstract. Yes, enable it. So this stuff's a little abstract, but it's important to understand. So remember intermolecular versus intramolecular? What was it?
Intermolecular was between multiple atoms. Intra is just inside of one.
Right, in between multiple molecules or particles, yes. And then intra is inside, between atoms within a molecule. Right, okay, good. So energy and change of state. So I told the younger class to envision themselves, this was kind of fun to do actually, and it worked. So envision that this room had a wall here and we were all shut in here together. And if we were at a low energy state and we were all laying on the floor in our little sleeping bags in nice neat little rows, we would say our energy's low, and what would we say about our level of order?
High.
Yeah, so then likewise, we would say what about or conversely, we would say, what about the disorder in that case?
Low.
Right, okay. So our energy's low and our disorder is pretty low. We are chilling. Okay, now at this moment, where are we? We're moving around, but we're not having like a dance party in here, right? We're sitting here, we're doing stuff. So our energy's a little higher, and how's our disorder?
A little higher.
A little higher too, right? And I also told them you could think about it like, well, I'll get to that in a minute. So now what happens if we all had 3 gallons of ice cream and 5 liters of Coke and a whole bunch of candy and, you know, yeah, it was like, you know, we had like the rave music going and, you know, we were really bouncing off the walls in here. So we would say our energy's really high, right? And our, what she said?
would be away from me.
Yeah, there you go, right.
And this kind of like two pop tarts.
Right. So our energy would be really high and our disorder would be really high. We'd be crazy disordered, right? So you can think about that as the particles within a solid, a liquid, and a gas. So if we were solid, we'd all be laid out nice and chill. And if we were right about now, we'd be like a liquid, right? We're moving, we're not slamming into each other, right? And we're not completely disordered. And then if we were having our rave party in here, it would be like a gas because we'd be slamming into each other and mosh pitting in the breakfast room. It'd be awesome, right? So yeah, I did a couple mosh pits in my day. It was way back when, man. It was fun. I had to get carried though because I was so little at the time. Get you in and out safely so you don't die in there. So anyway, yeah. So okay, now imagine this. Which one of the three states, being full of energy and having very little energy, being crazy disordered and having a lot of order, which one is going to take as far as the order goes, the organization and keeping things neat and organized, which one of those is going to be easiest to maintain, do you think? You think solid's easiest? Let me ask you this. If you walk in your house, do you automatically put everything back where it goes, or do you drop some things on the floor? Yeah. That's a personal question. So I was saying that when I lived at home, when I was a kid, my room was it was fairly messy from time to time. But when I got to college, I was packed into a smaller room. We had the option of getting a roommate or getting a single. And since I hadn't grown up with a sibling, I was like, I don't know about this. So I just got myself a single room. And the whole room was probably a little smaller than this room. And that was the whole everything. It was my desks, my closet, my bed. We all had a communal bathroom. But I was forced to be organized. Or even because the room was little, but if I didn't put stuff where it went, oh my goodness. Right? I mean, it would be a disaster. So I was absolutely forced by the nature of the space to keep it really, really organized. Now, so if I walked in, I would have put my keys exactly where my keys went. Because if one thing got out, everything got out, then you couldn't, it was just crazy. But this is a lot more space. And I will fully admit, when I walk in, sometimes I toss my bag and my keys on the counter. I'm not so forced in this situation to keep myself organized. So what do you think is sort of the natural state? Are we more likely to be disordered if we're not forced to be ordered, or more likely to be ordered if we're not forced to be disordered?
Probably.
Yeah, I would say if we're not forcing ourselves.
Rare cases, maybe the second one.
Yeah. So the natural bias is going to be disordered, just like we are. And when you think about the energy states, chilling on the floor, sitting like we are, having a rave party, which one of those is easiest to maintain?
I think
Passing out on the floor is easiest, right? Like you don't have to take any energy, you just lay there. So those are going to be your natural bias. Nature is going to tend to push you one way or another. And it's going to tend to push you to be a little messy and really lazy, right? So that's how you think about enthalpy and entropy and how they relate to how they relate to one another. So when we look at enthalpy and entropy and change of state, so we remember that enthalpy, we've been over this one a lot, is the total energy of a system, right? And entropy is a measure of the disorder. And if it helps you remember that the word entropy has an O, so when you're dealing with order and disorder, you can remember that one is the one that goes with order and disorder, whereas enthalpy is the one has an H in it, and that tends to go with heat, right? Because we usually see energy in these cases as heat. That's the other thing. So how are you going to be hottest? Having the rave party or laying on the floor? Yeah. Okay. So as your enthalpy increases, your heat is going to likewise, they're together, right? That's the measure, because remember, your temperature is a measure of the average, it's a measure of the average kinetic energy in a system. So if we're moving around a lot, it's going to get hot in here, right? Because you're measuring the energy of the system, and we have a lot more energy because it's the kinetic energy, and we're actually moving. Same thing's happening if we were if we were a substance and we were all molecules within that substance, if we're, moshing around in here and throwing each other at the walls and doing whatever crazy stuff we'd be doing, I've seen some things in my day, so we would be, obviously, that average kinetic energy is increased. We're going to be hotter, right? So then we get to this bit about your enthalpy of fusion. And then you have the entropy of fusion. And then you have these two, the enthalpy of vaporization and the entropy of vaporization. So you think of fusion as being things coming together, right? Well, so it says the enthalpy of fusion is the energy added during melting or removed during freezing. If you can remember that the enthalpy of fusion is taking energy out so that it goes back to that resting state, back to freezing, back to solid, then obviously the converse of that is going to be about adding energy to melt. We don't call it something different. So when you're saying the energy added to melt something is the enthalpy of fusion, that sounds weird. It sounds backwards. But it's describing that same energy that you would use if you took it back out that would cause it to freeze. Does that make sense? That part gets a little kind of weird. And then with vaporization, the enthalpy of vaporization is the energy added to a system as the particles separate and the substance vaporizes, or then your increase in randomness of particle motion as a substance vaporizes is your entropy of vaporization. So if you're dealing with freezing or melting, and then you're dealing with vaporization, you've got those two terms to go with it. Know what they are. We're not measuring them anytime soon, so, but know what they are. I'm sure there are some really interesting fields of chemistry and chemical engineering and probably even some mechanical engineering that gets really involved in that. I can't even imagine. So then this is an interesting graph. So I'll make this a little bigger so you can see it. So here we have temperature in Kelvin over here on the left. Okay, and your bottom is your energy in joules. So as you look, as this energy is increasing, the temperature is increasing right along with it, right? And it even says right here, here's your enthalpy, right? So your enthalpy is moving up the line. And this is your solid. And then look at the level spot. What's the level spot right here? Where it says going from solid to liquid. What do we call that when you go from solid to liquid?
Melting.
Call it melting. Okay, but what's up with the temperature?
All the energy is being used to melt it.
So your temperature isn't changing during the actual melting. Just like right here, your temperature isn't changing during what?
Because all the energy is being used to break the particles,
Right.
not to heat them.
So this right here is going to be your melting point.
That's also why when you're cooking something, there's a lot of water in it. Why once you get up to 212 Fahrenheit,
Yep.
it's just gonna stall.
Stays
until you
right
get all
there.
the water out.
Yeah, that's what I was going to say. When you get right here to this is your boiling point stuff. So yeah, you get your pot of water on the stove, and the hottest you're going to get the liquid water is what?
212 Fahrenheit,
100 degrees Celsius. You are not going to get that pot of water any hotter. It's not possible. Now, what about right above the water?
That could get hot.
That's hotter. What is right above the water when you're boiling it?
Gas.
Yeah, the water vapor, right? And you can see some of it. Some of it's visible. The stuff that's visible is not as hot. The stuff you can't see, whew. So that's when people get burned, because they don't see it. And they stick their hands or their faces over the pot. Never smart. But that's right there. You're not going to get hotter for this whole span of time while the change is going on. Same thing down here. And then you'll get this whole bit of equilibrium, right? And triple point and all of that. I've got some fun videos today. So here's your
See if they work.
Yeah, so here's your Gibbs energy. All right, we're back at this again. This was right before Christmas we discussed this, right? And this is interesting here. It talks about whether it's negative or positive, and that tells you whether or not the reaction is going to proceed. So if you have enough energy to, is it next? No. I had one with the little guys that was a teeter-totter, so I thought I had it for you guys. So imagine it like a teeter-totter, okay? If your enthalpy and your entropy are the same, they're pressing equally, it's not going to go. But if one tips to one side, then the other's going to tip to the other side, which you'll see as we get there. So for this here, here's your enthalpy and entropy. So what do you notice? Let's see. Here's your Gibbs energy, and here's your enthalpy. And you'll notice that they are what? How would you describe that?
Mirror.
Mm-hmm. Yeah. They're moving in opposite directions. Okay. So then we're going to give Professor Dave a go here because he has this great, is this not going to go? Oh, this makes me crazy. He has this great video on, talks about my cells in here. Here we go. And I will say before we start it, you ever been to, especially ladies, you ever seen in the drugstore, they have this stuff now called micellar water? Never seen it? Everybody's like, oh, you should use micellar water on your skin. He's going to explain what micelle is for you. And it's not as exciting as you might think. Well, maybe it is, but maybe it's not. All right, so he does a good job of explaining
the laws
this.
of thermodynamics.
He does a good job of explaining everything. Oh, I bumped him. Sorry, Professor Dave, in the middle of your song. Here.
I don't think you can do
Professor Dave
I
here,
love him,
let's
though.
learn
He's my
the
favorite.
laws of thermodynamics. He knows a lot about the science of Professor David Flake.
He's the best.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense. There is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation
Right.
energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists, it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing.
So think about that one for a minute. If you don't stop and pick up your room and put some effort into organizing it, what happens?
It gets messy.
Yeah, exactly. Okay. That's exactly where he is.
System, there is also a tendency to go towards higher entropy.
I hate when the
The
audio
classic
crackles up.
analogy is that your bedroom will over time become messy, but it will suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in state. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of the system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more ordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around, entropy. The third law states that a perfectly crystalline solid at absolute zero is an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a energy itself, but of how energy is distributed within a system. It is enthalpy, thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If it is non-spontaneous. So we can use this equation to see how a spontaneous process be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, with an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T. So entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the non-polar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water soluble due to the polar heads facing out. That's how soap works. And that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy storing processes. In this way, systems can defy entropy on the small scale. But the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension.
So when you see that at the store, when you see that micellar water, it's full of those itty bitty tiny little microscopic micelles, which have the non-polar tails in, and the polar heads out. And the whole thought is it's gonna trap the dirt inside and wash it off. So basically it's microscopic soapy water, but they're selling it as like some amazing new thing. Microscopic soapy water. So let's see. Determining melting and boiling points. So here's your enthalpy of fusion, entropy of fusion, okay? And these were the equations that go with them, which were in your book. And your homework tonight, so you need to look in teacher ease, because what I did was I wanted to show you guys two different ways. So you've got a lot of equations. what I want you to do is, it'll be listed on there, but it'll say like, do 1 or 2 of these or attempt 1 or 2 of these by hand. And then what I wanted you to do was find one of the various options for calculators. The reason I want you to do that is because it's good to know where they are and how to use them, because there are college kids in chemistry labs right now that are tick, 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 tick on their little calculators, because there it is. It's completely accessible. So attempt 1 or 2 to make sure you understand conceptually what's going on. Plug them into the calculator so you know practically how to use them, because those are tools, that's technology that we now have that makes this sort of stuff by hand good to understand, but not necessarily always something you have to work through completely every time, right? All right, so that's the mathy bit for today, and it's not too much because we're not going to get too deep into it. If you were in the college level class, you'd probably spend a lot more time on all the little intricacies. But conceptually, this stuff about pressure and state change is just as important as understanding about the enthalpy and entropy with state change, because it totally plays into things. So physical conditions like temperature and pressure can affect the state of matter. We talked last week, I think, about propane, liquid propane, right? It's under pressure, that gas under pressure becomes a liquid. And we talked again about how, if you've got all your molecules all spread out and you suddenly take that container and you decrease the size of that container, you're forcing them together, which is going to change their state. And if you continue forcing that propane far enough, under enough pressure, you'll get solid. That's how it works, right? So when pressure is exerted on a substance, it increases, it can cause the substance to condense. That would be coming together, right? Decreasing pressure can cause it to vaporize. So for some types of rock, decreasing pressure can cause them to melt, which would make sense, right? So phase equilibrium, we're going to do a fun little water bottle experiment in a minute. It's actually one of Cole's, it's his favorite thing to do with water bottles, but now you're going to understand what it is. What do you do when your water bottles are empty?
Yeah. Oh.
No, you do a thing with them. Yeah. So we're going to go over that. So when you have two-phase systems, so here we have equilibrium involving constant interchange of particles. So equilibrium. So here's a great graphic. I'm sure glad they evaporated. Hey, we're back. So it's this constant change of particles. And equilibrium occurs when there is constant movement of particles between at least two phases, but no change in the amount of substance in any phase. So think about that stretch that we saw, the flat stretch that we saw on the graph a minute ago about boiling point, freezing point, that level area. So you have a constant phase change right there. And it's not until those particles either pick up enough energy to move on, go up the next phase, or lose enough energy to move down a phase, right? So, but there's no change in the amount. So this is a closed system in this little flask, right? You got this closed system. These particles aren't going anywhere. They can't get out of that system. So there's no change in the amount. So vapor pressure increases with temperature. And here's a graphic for that. It's a short one.
After you've kind of seen the results of what happens when you start studying intermolecular forces, and we start making a little bit more of a condensed phase, such as solids and liquids, you're getting all these unique properties of solids and liquids. Liquids have quite a few unique ones: viscosity, surface tension, and one of the more unique ones is vapor pressure. That's a very special case, and that's probably another thing completely. So let's just think about it. If you take, or in a container, and you allow it to start evaporating, the space above the surface of the water will start getting water molecules. That means it's a gas now, and gases impart pressures. So as that builds up, what's going to happen is these particles floating above the water can go back into the water unless they're whisked away. So put a lid on the container, all the particles are trapped, so the water starts going back into the water phase, or I should say the water vapor goes back in. As this happens, you finally reach a state at which the exiting evaporation rate equals the entering condensation rate, and you reach what we call equilibrium. So when those two rates equal, you establish a constant pressure inside your container. That pressure is called the vapor pressure of that liquid. In case of water, you would say it's the vapor pressure of water. It's an example of what we call dynamic equilibrium, meaning when you look at the thing, you can't tell anything's happened. But in actuality, there are billions and billions of molecules leaving the surface of the water, and there's also billions and billions re-entering, and they are exactly the same rate. So there's no net change, but you have established what we call a vapor pressure. And that's hopefully a little bit more of a handle for you what vapor pressure is. We have other things to tell you later about vapor pressure in other videos.
So think for a minute about weather systems. What were you gonna say?
How do we measure vapor pressure? Like if you were to say, what's the vapor pressure of water? What would you say?
Yeah, so it's, you mean like what, huh?
Unit.
Unit, you just asked me the question and I wasn't ready for it.
Was it the KPA thing?
Yeah, it's pascals, I'm pretty sure it's pascals.
Kelvin, Kelvin?
No, it's not Kelvin, Think for a minute though, while I pull that up for you. Think about it as weather systems and rain versus sunny days. Think about the pressure outside. Can you draw any relationship there?
Yeah.
Explain what you're thinking.
It's the same way, except the lid is like the size of the globe, and the lid is the atmosphere. It's water.
Oh, mercury.
It's so heavy. Mercury.
Yeah, millimeters of mercury. There you go. Yeah, like it's a barometer. Same concept there. Or torr.
Okay.
Torr was the one I couldn't come up with in my head there.
It's like the water is in a lake, and then it gets hot enough, or it just releases enough energy, it starts to float up, makes clouds, and the clouds get so heavy that they rain down.
Right, exactly. It's the
Except
same.
It happens a lot faster.
Yeah, it happens a lot faster in this container. Right. So you can also consider it when there's high pressure, it keeps the water from joining up in the air, right? Which means that you're not going to get rain. Like when we have high pressure days is not when we have rainstorms. It's the low pressure days. And it makes a lot of sense that also the temperature tends to go along with that, right? Because if you heat something up and a gas expands, then the gas above your water is not going to have as much pressure. I mean, it's expanding is going to have more pressure. So you can think of it that way. And then this thing that I'm going to show you, well, we're going to do it in a second. With the water bottles is going to make it visual right in front of your face. So here's your phase diagram. You guys saw these in the book, right?
Yeah.
And there's something right here called a triple point.
Yeah.
Right. And then there's something over here called a critical point.
Yeah.
And I did find good graphics for both of those because they're hard. It's hard to conceptualize, much easier to see it. So here's your gas liquid equilibrium. So we're gonna do this. There's two different ways to do this. You can do this with straight up water, which is usually what coal does with it. And you can also do it with adding a little alcohol. What do you think will be the difference between the alcohol and the water? Don't know. This one, this one was partially empty and hanging out in the schoolroom. So we're gonna use it. And then one of these other ones we're just gonna get. Okay, so take the label off, Cole, and then explain what you're doing, okay? I'm gonna flip this camera around here. Yeah, get peel the label off so we can see a little better. This is a party trick. It's a great party trick. All right, so how does it work? What do you do?
And you put the lid on, make sure it seals.
Okay.
It's a little loud.
All right,
Seal.
seal, you can go in tight. So he's basically first, that one not work, I have others. Okay, so wait a minute, before you do that, we empty the water out, but there's a little bit left. See a little drops? Hold it up so that they can see real good. There you go. Twist it as much as you can.
Keep going at a certain point, the cap will pop off, so don't do that.
You don't go too far. All right, so show everybody what you've got. Now he's twisted it, so what's happened to the pressure in the bottle?
It's increased.
We've increased the pressure.
I'm gonna move the middle so y'all can see it.
Yeah, come, see if you can put it,
You gotta look close.
see if I can get you on the, wait a minute, hang on, wait a minute, Cole. See if I can get this where they can see it. No, I can see here. You're good.
And then you keep the lid off. And
Open it.
squeeze
Ta-da! What do we have?
Water vapor.
Water vapor is exciting. Okay,
It remains.
so why did that work? The remains. Why did it work? Who can
It
tell
might
me
actually
what
work the second time too, like kegerator. I think I got it to work twice once. You just unscrew it and then like blow some air in it and then try it again and it might work.
So what, but why did it work? What happened?
You
The pressure was increased so much, it turned into a gas.
Right, increase the pressure so much that you forced some of that water into a gas. Now, this time we're gonna do it. What'd you say about the kegerator, Jay?
Do you want to do a field trip to the kegerator?
Weren't you pressurizing it right now?
Yeah.
We can do,
What you're talking about right now.
yep, we can do that. Give me 1 second. We'll do this one and then we'll do that. We're pressurizing the kegerator because we just put brand new cider in it. So back on our discussion. All right, so this is the same idea. I'm just gonna take a little, this is 99.9% technical grade isopropyl alcohol. So I'm just gonna put a little bit in the bottle.
Good stuff.
It's like-
That's the good stuff, yeah.
Good stuff.
This is what I have been de-germing everything with since it all began. I was gonna play seriously. All right, so
It's been hard.
we're gonna put this in here, put the lid on again. All right, now what I'm gonna do is I'm just gonna twist this around a little bit because what I'm trying to do is get the alcohol to coat the whole inside of the bottle. Okay, there we go. So it's got pretty much all the surfaces. And I'm gonna empty out the little tiny bit that's left. And now we're gonna do the same thing. Anybody wanna do it this time? Wanna do it, Michael? All right. Make sure that lid's on really tight. Now watch and see what we get this time. Oh, wow, the helicopter's super low.
I think that's the project one that got that.
Yeah, it's probably that guy with the,
Wow.
all right, so Michael's about ready to do the top. You gotta do the top fast when you do it. Yep, are you ready? You watching? Woo! But look at his bottle, look.
Oh, squeeze it, it'll pop.
Now, did we see more or less of a cloud? Why? Why did we see more? Oops, sorry, don't do that. Don't do that. So, I know, it was really weird, wasn't it? I don't know why it did that. So why did we see more just then? Anybody want to guess? No clue. So let me ask you this. If you put, hold on guys, we're gonna take a trip to the kegerator real quick, but if you put a cup of alcohol on the table and a cup of water on the table, which is going to evaporate first?
Water?
Alcohol.
Alcohol evaporates really fast. Why?
Less dense?
Well, it has to do with the pressure too. I mean, think about it. It can, well, there you go. So because it is going to react to even lower pressure, even more of it is going to come out. So this is that video. Same thing we just did. This guy talks about it being a party trick. And we'll go over and look at the kegerator real quick. See, same thing you just did. Cool party trick. So he basically is going to show you what we just did. Ta-da. And he's proud of it. So let's take a trip into the pub real quick because there is something cool going on in there. Same thing. Jason has a good idea. We'll follow him. You get to teach my class for a minute.
I think.
You're all right.
I think this bottle is pretty well ruined.
It's okay.
Yeah. this bottle's good.
Ta-da. Ta-da, ta-da. You're good. Yes, a lesson in, is this a lesson in
So
bartending?
this is a sort of, so this is a kegerator. You guys heard of kegerator? It stores beer, but you can also use it to put carbon dioxide into the beer to make it fizzy, right? It's like if you have a Coke and you open it up and it's all fizzy, that's carbon dioxide bubbles. You get that by taking carbon dioxide at a very high pressure and pushing it into the liquid. So if you look in the back here, I got a tank here, CO2, and there's a regulator on her. And if you can look, it's pushing at 25 PSI. So I'll show you the inside. So this is the keg.
This is so funny. This is the best homeschool
Cool.
lesson
So it's
ever.
5 pounds. Sorry, it's 5 gallons, right? The red line is
It's
the
a lot
gas.
more than 5 pounds, yeah.
So this goes straight to the tank back there. So it's 20 pounds per square inch of carbon dioxide going into here. And this is just a tube. It's just a tank full of apple cider right now, hard cider. And so right now the valve is closed. So it's all a closed system right now. Like there's a little bit of air at the very top where the top of the liquid is, and this is going into that. And we are pushing carbon dioxide into the top of that beer, which is it's forcing carbon dioxide into the liquid. So there's that exchange of liquid going evaporating and condensating, but it's happening at a faster rate with the carbon dioxide under pressure.
It has to be insulated so nothing can escape, right?
Right, because it's a closed system right now. If I were to open it, it would go everywhere. But if you open it, you're also, because you have pressure going into here.
Yeah.
Now, most of the time, they just do this so that you can get the beer out, but
Yeah.
you can also use it to put carbon dioxide into the beer. You can do both things.
Which is what we do to make the cider fizzy.
Yeah, so this is pushing carbon dioxide into the top of the can, and at the bottom of this, there's a straw. It goes all the way to the bottom. So it's pushing all of the air on top against the liquid into the bottom, which forces the beer up the straw.
Yeah.
So when you do that,
This is seriously the
It
best
pushes it
homeschool
out.
lesson ever.
so yesterday there was no bubbles. Like I just started it yesterday, but today there's some pretty good bubbles there. So we were gonna debut it tonight, but
Yeah.
so it's a little bit earlier. But,
There you
but
go.
as you can see,
No, it is fizzy. I'm
there's
bringing it
fizz,
so you can
right?
see it.
Like that came from the
Interesting.
carbon dioxide.
Oh,
So that's
thanks, Jason.
how a keg works.
Fun lesson. So now y'all can go.
It's called forced
Good job.
carbonation.
Awesome. Thank you, hon. There we go. All right, cool. That's interesting. I don't think they do that in public school, do they? Are you sure? They might, they might just like bring out the keg. There's one in the teacher's lounge I heard.
Probably.
Probably.
That one.
Should be if there isn't. How about that? There we go. Woo, that's a chair.
That was 100% your fault.
100% your fault.
Yeah.
It's not your fault.
You're trying to blame that on me.
You hear this guy? Oh my.
I do, man. Craziness.
I didn't see Ethan touch it,
I
but.
saw Michael smack it
I
down.
didn't.
So when we
I
did,
almost smashed on him.
Yeah, I did.
so when we did the alcohol, we got ourselves a better cloud. So if we look at this here, this is your solid liquid equilibrium. Okay, and then I was trying to find some visuals for you of these different types of equilibriums, because some of them are probably more simple than you think. You've seen it 100 times and just didn't realize what it was. So for the solid liquid equilibrium, and this one is, I think you said the weird 90s voice or whatever it was.
They'll bring out like, it's like a.
Solid liquid equilibrium. Take 10 milliliters of water in a beaker and add 10 milliliters of ethyl alcohol into it. Water alcohol mixture, add about 2 grams of iodine crystals and stir well.
I did, yeah.
A reddish brown color appears in the solution, which then turns violet. The temperature is kept constant. After some time, the intensity of the color of the solution does not change. There
So
is
at
no
all, when it's
observable
not changing
change
anymore,
in the amount of
that's
solid iodine that settles down. The system has attained equilibrium.
That simple. So then,
Solid
no,
liquid
go away, go away. In this case, this is your solid gas equilibrium. Same kind of concept. they're using the iodine crystals again, because I guess these are really popular for this example. This lady has an accent, but you can understand her.
Let's consider a few crystals of iodine placed inside
They'll say
constant
iodine.
closed vessel at room temperature. The iodine molecules start getting converted into vapor state. The region inside the vessel starts turning into boiling. As time passes, the intensity of color increases. Finally, at equilibrium, rate of sublimation, that is a conversion of solid into vapor, of iodine becomes equal to the rate of condensation of the vapors. Thereafter, the intensity of color in the vessel remains unchanged.
Same thing. When your color doesn't change anymore, it's done. So those are two examples. You've probably seen that 100 times and just not realized what you were. No, stop. Why do they keep coming back? Now this is the cool one. So you guys read about triple point. What happens at triple point?
All the states at once.
Right. It's the perfect temperature, pressure, and you can get all the different states. This is cool. I would love to actually, I haven't seen this firsthand and I would love to because this is super cool. Hey, he's licking my hand. Oh, come on. Here we go.
Outrageous things.
It's outrageous.
Students at the University of Manchester in the United Kingdom were trying to identify this liquid when something very unexpected happened.
That's cool.
This is one of the reasons that I love science. It is the most unexpected things.
I have no idea what's going on in this video. Can someone please explain to me how this is somehow boiling and turning into a solid at the same time?
Over 5.5 million views later, it's time to figure out just
I know.
what this substance is.
What these guys have stumbled across is a very specific pressure and temperature, which scientists refer to as the triple point.
Which is the perfect temperature and pressure at which all three of these solid, liquid, and gas phases can exist. It takes just a really tiny change in temperature or pressure to flick between one or the other.
So, how did our student scientists stumble across the triple point?
It looks like water in that flask, but actually it's something called cyclohexane.
What they're doing here is actually vacuuming what we call the headspace of the flask, which is the gas that is just above the liquid. Now, because that contains cyclohexane molecules that have evaporated off the liquid layer, by removing that, we're changing what we call the equilibrium.
The system wants to restore this equilibrium, and that means that you get more and more cyclohexane molecules evaporating out of solution. But it takes energy to do this, and as a result, the remaining cyclohexane drops in temperature and freezes.
So the gas at the top of the flask is pumped out, disturbing the balance and making the liquid boil. But boiling needs energy, which is taken from the liquid, making it freeze. Then what happens? Ellen?
Now, it's a solid, there's no more boiling and there's hardly any evaporate, and all of the energy is just conserved. But a little bit of heat gets drawn in from the room, which means the solid turns into a liquid, which means the whole cycle starts again. From solid to liquid, to boiling, to gas, back to solid. The cycle goes on and on and on and on.
That's cool.
It's very cool. It is super cool. And I think I told y'all before, but one of my favorite things to do is when I'm doing canning, you get the same sort of thing where you've like if you have soup in a can in a mason jar and you take it out of the canner and put it on the counter, you'll hear the little vacuum. It'll all go down, but it'll be sitting there on the counter and it's still boiling. There's bubbles moving all through it and you can hold it in your hand and it's still bubbling. And that has to do with the fact you've got this vacuum above it now, just enough heat that vacuum above it is allowing all the gas that's within it to start escaping. So the gas gets up in it and then that causes more pressure and it pushes back down in it. And then this thing keeps going on and on until it finally gets cool enough where that's I don't know, cool enough where it doesn't become a big process anymore. But does anybody have a canner, like a big pressure canner at home? It's really fun. They're super loud, but it's really neat to watch because it'll just sit there on the counter. You can pick them up in your hand and they're boiling. It's really interesting. So the last thing, they're super loud because they have a weight. You have a weight on top of it. And like the weight I have gives a certain PSI and you can turn it depending on whether you want like 35 pounds, 20 pounds, whatever. And you sit the weight on the little steam stem and it goes as it bounces up and down for 45 minutes or whatever. So it's very loud, but it's super cool. I did want to show you critical point, because as neat as triple point is, critical point's equally cool, maybe even neater. And these guys engineered this awesome container for their experiment that is really, really interesting. I love it. It's like engineering meets chemistry.
Every substance
He's very
has a
German.
critical temperature and a critical pressure. When a substance is subjected to temperature and pressure that both exceed these critical values, it enters what is called the supercritical state. Any pure substance can exist in three phases. Can be a solid, a liquid, or a gas. We can draw these phases using a temperature-pressure diagram called the PT diagram. This graph shows the location of the different phases of a pure substance in relation to pressure and temperature, with pressure P on the vertical axis and the temperature T on the horizontal axis. The three phases are separated from each other by so-called separation lines. We have the sublimation line, which divides the solid and the vapor phase. The sublimation line ends at the triple point, which is the point where all three phases coexist. There is a melting line between the solid and the liquid phase, and the vaporization line between the liquid and the gaseous phase. The vaporization line ends in the critical point. The temperature on this point is called the critical temperature and usually gets designated with the symbol TCR. The critical pressure has the symbol PCR. These values, together with the critical density, are characteristic for each substance. With pressure and temperature that exceed the critical values, the substance will become supercritical and the differences between the liquid and the gas phase disappear. Let's see how this works in practice.
This thing is cool.
For this experiment, we made our own pressure tank. It has a thermometer, a pressure meter, and a pressure reliever. We also have some dry ice, which is carbon dioxide in the solid phase, a heating plate, and a heating base. We put some dry ice into the tank and seal the tank.
I love this tank. This is such a cool tank. Look at that little
As
thing.
the pressure tank is completely sealed, the pressure builds. The dry ice starts at a low temperature, but with the rising pressure, it soon turns into a saturated liquid vapor mixture at about 40 bar and 5 degrees Celsius. By applying heat to the tank, we increase the pressure and temperature towards the critical point at constant volume. CO2 has a critical temperature of 31.25 degrees Celsius and a critical absolute pressure of 73.9 bar.
Look at that.
So we want to heat up the carbon dioxide to its critical temperature, and because the volume of the tank is constant, we can also build up the pressure. As the pressure and temperature reach the critical point, the distinction between the liquid and gaseous carbon dioxide becomes less visible and eventually disappears.
Yeah, watch the line where there's, look at that. It just kind of poof. You can almost, it's almost gone.
The phase boundary between the liquid and
That's
the gas
cool.
vanishes. The CO2 is now in a supercritical state. To return to a state below the critical point, we will cool the carbon dioxide and make it reappear in the saturated liquid vapor mixture. By removing the heating plate and letting dry ice on the aluminum cylinder, we can observe that the liquid vapor interface suddenly reappears as the temperature decreases.
Look at that. You can see the boundary show up. Isn't that
We
wild?
return to the saturated liquid vapor
That is
mixture.
cool.
Yeah.
Supercritical CO2 is used in a variety of applications, for example, to remove caffeine from coffee beans.
Yeah, caffeine from coffee beans. That's how you get rid of it. Supercritical CO2. So here's your definitions that you guys had. You guys can probably come up with some of these. So what do we have for, what did you guys write for molar enthalpy? What'd you get, Abby?
The energy added to a substance to make it change from solid to liquid.
There you go. Yep. So the amount of energy needed to change 1 mole of a substance from a solid phase to the liquid phase at constant temperature and pressure. There's always going to be constant temperature and pressure in like pretty much most of these definitions. Also known, you may also hear it as molar heat of fusion or latent heat of fusion. All right, how about molar enthalpy of vaporization? Based on the previous one, what'd you get, Abby?
The energy added to a substance for exchange from a liquid to a gas.
So same thing, it's the amount of energy needed to change 1 mole of a substance from a liquid to a gas. And usually this is going to be in kilojoules per mole. And this indicates the energy absorbed by the system to get the molecules into the gas. So phase, what do we have for phase? Who has a definition that's not Abby? Anybody not Abby? Michael, what you got?
The uniform part of matter.
There you go. Okay, what'd you get, Cole? Anything different?
Yeah, something.
Okay. Some of mine are a little more extensive. So it's a distinct and homogeneous state of a system with no visible boundary separating it into parts. So water, H2O is such a common substance.
The definition I have
Yep.
basically just the reciprocal of the one that was in the.
Yes, exactly. Yep.
You did say our own words. And
Yes.
That was my own words.
Yes, yes, yes. I like your own words. Those are good. Oops, I just clicked equilibrium. So equilibrium, chemical equilibrium is the condition in the course of a reversible chemical reaction in which no net change in the amounts of reactants or products occur. All right, how about, oops, those didn't go away. They were supposed to be disappeared. Anyway, vapor pressure, what do you have?
Vapor pressure is the partial pressure being exerted by vapor that is at equilibrium with its liquid state.
There you go. Or the tendency of a material to change into a gaseous state.
Yeah.
Right? All right. And then, did anybody try and describe phase diagram? What'd you do, Abby?
A graph showing a substance's physical state versus its temperature
Yeah.
and pressure.
Something similar like that, Michael?
Yeah, the graph that tells us the relationship of state of matter.
There you
and
go.
temperature.
Good. And triple point, I think we all just saw, and Abby defined it earlier. You get all 3 existing. What do we get for a critical point? What'd you get, Cole?
The perfect moment at which pressure and temperature form one single phase.
There you go.
But it's not a perfect moment, isn't it? The perfect moment and then everything.
It's a point at which a substance in one phase as a liquid has the same density, pressure, and temperature as another phase, gaseous. Water and volume, the volume of water at critical point is uniquely determined by the critical temperature, this says. So that's an additional thing. Blah, 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 blah. So I want to show you for tonight, I want to make sure that you guys remember to do this right. You can use the one in your book, the one in your binder, the copy in your binder if you want. But, oh gosh, I gotta move this so I can get, where's my mouse? Oh, did you ever lose your mouse on the screen? Gosh, it's
Yeah, you have a white and black background. So.
I know, but it's just like I know, it didn't want to go. There it goes. Okay, it did not want to play with me for a minute there. It's freezing. That's weird.
Michael, you are.
Oh, wait, my God.
Everything's bad in this world.
What are you doing?
I dropped into my eraser, my camera pencils, and now it's just gonna fall out of here. No, that's actually take it back. It's not a piece I have.
You're a mess.
I'll show you there's a giant clump of hair on your seat.
Is it what?
Giant clump of hair.
That's really gross. Is it my hair? It's usually my hair.
It's definitely not. I don't think. What is
That's
that?
nasty.
That is a sizable piece.
Dude, you're having trouble.
You want it?
What is this?
Yeah,
You want it? Yeah. Well.
Okay.
It's, yeah, I'm gonna
Your
go
lesson 19, no, not lesson 19, 20.
I didn't mean to. I'm sorry.
Okay, when you go into teacheries and you go, when you go into teacheries and go to lesson 20, you're gonna see this right here. And you see where it says your updated alternate homework assignment? So this is the one I want y'all to do, and it's in,
Alternate homework assignment?
yeah.
Okay.
So I'm making your life easier. Oops, somebody commented, was it Shannon or Sydney? I couldn't see that earlier. It's Professor Dave. Oh, it's Jack. So here are your new instructions right here. In each section, attempt problems A and B by hand on a separate sheet of paper, and then search online for a gas law equation calculator. Answer the remaining problems in each section using the calculator, and then tell me what app you use. Like give me the URL or tell me the name of the app if you have it on your phone or whatever. So you're going to do A and B. You're going to attempt to do them by hand. And this will be with the homework that you will have just read. So some of this stuff is, you don't even know what these equations are yet, but you'll get there. You're going to do A and B by hand, and then you're going to do the rest using a calculator. There are tons of calculators. So when you bring me your homework, just put all your answers on the separate sheet.
So for the phase diagrams, I was just wondering, is there like for the line between the triple point and the critical point, it was like just draw it with a curve.
Yeah.
So I was a little confused. Like, is there a specific?
Are you on? What are
way
you?
that-
Are you looking at?
On the second part of
Yeah, the question you ready to draw on.
Yeah.
Yeah.
So hold on, I'm opening it right here. Which one is this? Don't know why suddenly my mouse is being stupid, but it's annoying me. Okay.
And then same with like drawing the barrier between the solids and the liquids. It was just start at the triple point and go up at a slight incline.
Yes.
Yeah.
I don't know if it's like
Why did this just open? Hold on, I'm trying to open the right document for you here.
watch.
Maybe. Here we go.
You're able to find another figure.
So we're right.
You.
Whoops. So this is so for your book. These came out of your book basically. And so this is the phase diagram that they had as an example, is as the answer or whatever for this. Is this kind of what you have or similar?
Yeah.
You mean beyond the critical point? What do you do with the line? Is that what you're asking? You can stop it there like that.
That's a lot like what I have.
Yeah, as long as you have this number here and this number here and they line up. Yes, so where you've got, what's mattering is your number here
So
lining up
it's like a graph.
and then your number here and
You
here.
can.
So is it
plot
just a
as many
straight
points
line?
as possible. Same one.
Watch your head.
Yeah, we found one in the college workbook that was not a straight line, but it just, if you have the time, you have to go through every single plot point and say, at negative 77 degrees, it's this, at 76 degrees, it's this.
But we weren't given that information.
It would have, yeah.
And even if we had it, we're picking it.
Yeah, so like I've always said, homework is about effort. What can you find? And you please use every resource, look stuff up. I mean, that's the point, right? That's the thing now that's the thing that I always try to get across is that, what's he saying now? And now I'm stressed. Oh, you're fine. So information is so ubiquitous these days. If you want to know any fact or get a graph of that, you can obviously look it up. It's not hard. It's in our pockets, for goodness sakes. So what's going to be important for you guys as you get through college and get into careers is going to be less what you know, like all the stuff you know, and more how you manipulate what you know. So if you understand how this graph came to be, what the different points on the graph mean, and that matters more than, how am I saying this so I don't sound terrible? That matters more than being able to spit out all the numbers, because you can always look up the numbers. Like they made us memorize capitals of all the European nations and it doesn't matter to me right
What's
now.
the capital of Hungary, Mom?
Budapest. But it doesn't matter to me. That means nothing in my life. If I wanted to know, I could ask that thing over there and she would tell me. What matters more is that I understand maybe how Hungary's history relates to other parts of Europe, or what we can learn from Hungary when dealing with our own system. That matters so much more than all the little facts. So certain things you want to know because you just want to know them. Like we're going to do this ideal gas law coming up, and that's the PV equals nRT. I haven't used PV equals nRT in a mazillion years, bazillion, even a word that doesn't exist. Because I mean, I was younger then, but until this class, I haven't touched it, but I know it, because that's a concept that when you have it, you've got it. So it's more about making sure you understand the concepts. I'm more comfortable with you guys making sure you know the concepts and you know how to use the equipment in the labs. And you know how to take good notes. You know how to take down good data. You know how to manipulate and interpret your data is much more important to me than memorizing everything. That's why I said write down your formulas on an index card. Because if you were truly a chemist working in a lab, you probably would memorize it because you use it all the time. But the ones you don't use very often, you'd pull out your phone just like everybody else does. I mean, everybody else does, right? We don't even know how to get anywhere anymore. You don't have to know how to get anywhere anymore. You just ask Waze to take you and she takes you. I mean, it's not. I used to, my first like real job that I worked for some period of time was I worked for a company that did entertainment. So it was like clowns and characters, and I'd go to birthday parties and I'd make animal balloons and stuff, whatever. But I had to drive all over the place. And you had to call people and say, how do I get to your house from wherever? Oh, I live in Virginia Beach, you're in Chesapeake. If I get on 64 and I go west, how do I get there? They would have to tell you how many miles to the exit, when you get off the exit, when is your next turn? Is it left or right? What's the name of the intersection? How far is it? I mean, we have to do any of that. So
Well, I remember Dad had a map of the Xterra for a while.
yeah, he did. He had an actual Rand McNally map book in there until not that many years ago.
Yeah.
So it's more about getting your feet wet with the concepts. If it's something you decide you love, then you're going to dig into it. You're going to learn all about it. If it's something that, chemistry I need for my high school credit so I can move on with my life, then you're going to understand the basics of it and move on from it, because that's the way things are. There's a lot I couldn't tell you about that I had to go through in high school. So yeah, that's the basics for that. And then for your homework, just be sure that, like I was saying, I want you to use the calculator, because I want you to know how to use them, because I'm pretty sure that's all there are in classrooms right now in college. So questions? You have a test coming up. I can turn off my screen share and tell you what to study.
Yeah.
All right, let's do that. Stop share. I'm gonna stop this one too.
What is Jack's name? Oh,
Dr. Pepper. What else would his name be?
No, there's something more. Plus Subway, I think.
Oh goodness, only knows. Goober. All right, good. That's gone too. All righty. Where was my thing? So let me tell you what to study. So you've got your test for chapter 11, whatever chapter this is, yeah. 11. And you will need to, be ready? Yeah. Study the following concepts. Oh, there he goes. Sorry. Yeah. So you're going to want to know your terms with regards to things like freezing, melting, all that kind of stuff. Freezing, melting, condensation, sublimation, deposition. Know what they mean, which phase to which phase, right? Most of you guys could probably do that one in your sleep. You're going to want to know about intermolecular versus intramolecular, what that means. What's this one? Oh, know what dipole is. Remember we went over that last week, right? Pulls one, positive charge pulls one to flip, and then they all flip. But you're gonna also want to know what's, hang on, we'll get there. Know about water and hydrogen bonds. And London dispersion forces. So we discussed them a little bit last week, and I think there was some confusion on the homework too. So I think what happened is I think that look it up thing backfired for some of you, because there was a sentence when you Googled that pretty much implied that the London dispersion forces were strongest, but the hydrogen bonds are strongest. The London dispersion forces can be strong, and it does depend on the size of the molecules that you're dealing with, but they're so temporary that it's almost like a negligible thing. They're constantly switching and changing. So they're there, but they're very temporary. So if you want to know your strongest bond to keep in mind is your hydrogen bond. Does that make sense? Yep. It was so funny because I was like, why did they all type this? So I started Googling things and then I found it. It was like in the top blurb before you see the whole article. And the way the sentence read, I was like, oh yeah, if you didn't read the whole article, this looks like so yeah, it happens sometimes, you know. That's how you get to the answer. Know about liquids and surface area. Know about, we talked about enthalpy, entropy of both fusion and vaporization, right? We went over that today. So be sure that you can define those, or at least would recognize the definition correctly. You have two short answers. One of them, you're going to need to explain to me how temperature and entropy are related. So think back to the bouncing around this room, more disorder, more kinetic activity.
Temperature and
entropy. So as your temperature goes up, obviously your entropy is going to go up. But I'm going to want you to explain to me why. I mean, you can just say, yeah, they go together. That's not the most thorough answer. I know all of you can do more thorough than that. Explain how to, okay, did that one. Know the definition of equilibrium and vapor pressure. Be able to explain a triple point. And then be sure that you can recognize the definition of critical point.
I'm hearing shouting, and the only word I understood from that last bit of shouting was purple.
Yeah.
Purple. All right then. I don't remember Spanish for purple. Is it violeta or something like that, or maroon or something?
There's multiple different ways.
That's what I figure. There's usually multiple different. We have a lot of words for purple, don't we? Oh, my gente. Okay, good. I don't do the Spanish, but I've learned so much of it just sitting here listening every week. It's funny. I understand half of what she's saying. All righty. So that's the thing for you guys to look. Be sure that you pull your homework off Teacheries this week, so you don't end up doing extra unnecessary work by hand that you otherwise would not need to do. We are approaching the time of year when you need to start thinking about your final project.
Oh God.
I know it's months away. Sydney and Ivy were going to work together, but obviously that's not going to happen now. So Sydney may or may not be up for a partner. Maybe she is, maybe she isn't. I don't know. But it should be interesting to see what you all come up with for sure. What else do we have? Do you guys have questions? Do you know what you're doing? Are we good? We're moving on.
I think yeah, I get it.
You get it? Good enough for now? You're tired today.
I am. I'm all best.
No, I get it. I had one class I couldn't stay awake for in college ever, no matter what. And I cared about it. And it was really important. And I just couldn't. So it was like a rhythm thing. I tried so hard, everything I could think of to change a rhythm. Didn't work. I was going to say something too, and it just went out my head. I don't remember. So just, just this week, go ahead and
Weeks until the final project.
Weeks until the final project. Good question. That I can answer. So if I go and I look, move, right? Let's see.
Can you bring me my science? Oh, are you going over there? No, it's okay.
Lesson wise, we have, where are we? We're here. We're 19. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 lessons. 13, 14 lessons, but there are, I think, three off during there because we're We have off for spring break in the mid, and there's 2 weeks in a row for spring break. Because I have to do Holy Week off every year because I'm usually just way overwhelmed with stuff at church I have to do. And Holy Week and public school spring break are back to back. So if they're back to back, then we're back to back. So we get a 2 week break at spring break. And then we also have one there's a winter break on.
So they have like almost 20 weeks.
Yeah. And there's a winter break on this 16th of February too. That aligns with public school.
Wait, there's a winter break?
It aligns with the
There's
public school
Christmas
winter break.
And then also winter break.
Oh.
Yeah.
That's why winter is the best season.
There you go. That's why winter is the best season. I'm with you.
Summer is the worst because it's hot in the club.
I hate it when it's hot. So I'm going to be sure that I put in your weekly email about that, watching for the homework. And then if there's anything else you need, y'all let me know. And I'll tell these girls on Zoom. We'll see them later. All right, Shannon and I guess Jack. And did I say Subway? All right. What do you need help with, Shannon? You just losing it over there? Help. 3 to 4 months before fine. You'll be fine. No, you're going to do fine. So, Shannon, you can call me anytime if you need help. Always. Don't worry. We'll go over stuff. If you need extra help with anything, all you do is ask. You're funny. All right, you guys. I'll see y'all later. She's home.